In this video, we're having a look at the way in which the spectra of stars is used to put them into particular groups. In other words, to classify stars. A lot of the important work with regard to classifying stars was done at Harvard University around about the early part of the 1900s, and it was done with the supervision of a guy by the name of Edward Pickering. Now, up until that time, what would happen was that the classification of stars was based on the spectrum of stars, but was based on what they thought was the presence of hydrogen, how much hydrogen they thought was on the star, and the complexity of the spectrum. To give you an idea of what I mean by that, if we have a look here, this is the sun or a star, and what happens there, as we know, is that it's giving out, as a black body, it's giving out a continuous spectrum. Around the outside here, we have the presence of an atmosphere, if you like, of the hydrogen and the other substances that happen to be present on the star. When the light from the star comes through that atmosphere, some of the atoms absorb the certain frequencies, and as a result of that, we get these dark lines. So these dark lines, as you may know, are absorption. They result from the hydrogen, in this particular case, the hydrogen atom absorbing an electron and being kicked up, so to speak, into a higher energy level. Now, when it comes to these lines that are in the visible spectrum, we're talking about the Balmer series. One way of representing those is like a photograph, which was common at that stage. More recent developments enable us to have what we call these tracers, and they're a more effective way of quantifying the intensity of a particular wavelength. So to see what the classification tended to look like, here if we have a look, this was the group A, had this kind of shape, and this absorption here of hydrogen. These spectra were, in fact, or the stars were classified in letters from A to Q. So it was quite a lot, quite a group of these. So this is A, this is B. Again, you can see here we've got the characteristic hydrogen spectrum, the Balmer series. And a lot further down now, because we've changed the system at all, we've got group F, and with group F, we've got a different shape of the spectrum. We can see the peak here is in a lower frequency band. This is the higher frequency, slightly lower frequency, the red area there. So we've got a shift, if you like, in the shape of the curve. That's important to realise. But again, we've got what seems to be less hydrogen, but that's not necessarily the case. So this is F, G. Again, we've got a different shape there, and K, another level of K, and M. By the time we get to M, you can see that we've got a whole lot of other substances, and all of these variations in intensity, they are the results of other elements and even compounds being present in the atmosphere of the star. Things changed. Now, Annie Jump Cannon was working for Edward Pickering, along with quite a number of other women who spent a great deal of time looking at the photos of the spectrum of the stars. Here they are again. He was very proud of his group of women doing the hard work. But Annie Jump Cannon, she was the person who ended up constructing the new system. There she is, as you can see, she's got the plates there. She's looking at her the photos, the photographic plates of the spectras or the spectrums, and here she's got the microscope there. So she was responsible for the classification of many hundreds of stars. What we need to do is to keep in mind the way in which the spectra are produced. Now, here, for example, we've got cooler hydrogen. So when the waves of light coming from the sun or the photons come through here, when this electron is excited up into this next energy level or the next, what happens is that we get spectral absorption bands or lines that are in the ultraviolet part of the spectrum. Here, where the electron is in the second energy level, now that would be the case when the atmosphere is hotter. So you remember that when when we have a look at the various states of matter, the hotter a substance is, then the more likely it is to exist in the form of plasma, and that means a separation between the nucleus and the electrons. So what it turns out is that, what it turns out to be, is that the hotter our hydrogen, the further out or the greater number of the hydrogen atoms are in the, are in higher energy levels. So a really hot star has much more hydrogen atoms in with the electron in an outer energy level, and what that means is that you don't get absorption in the Balmer series. Okay, you get here atoms that are like that, they get absorption in the Balmer series, but these ones don't. Similarly here, if the hydrogen is cooler, then we get absorptions that are in the ultraviolet region. Here, they would be in the infrared. So what that really meant was that the level of absorption here by the hydrogen atoms, in fact, the spectrum that we get for hydrogen was an indication of the temperature of the star. So this is what Annie Jump Cannon did. She rearranged the classification. Instead of going from A to Q, she simplified that. She reduced the number, so we didn't have A, B, C, D, E, F, all the way down to Q. We only had this handful. And if we go now to have a look at these spectra, we see here, for example, the hottest stars. The hottest stars, first of all, have got a high level of radiation coming in the shorter wavelengths or the higher frequencies up there in ultraviolet. Down here we can have we've got some hydrogen, we've got some Balmer series absorptions. Further down we get to the B group, again where we've got absorption here in the hydrogen spectrum. We're getting more absorption in helium as well. But then when we get to A, we've got even more absorptions that are in the Balmer series. So what that indicates there is that the majority of the electrons now in hydrogen atoms are in fact in the second energy level, and up here they are in perhaps in the first, in the further out. They're in further out from the in higher energy levels. So we get now down to the even cooler ones. We've still got a little bit of hydrogen there, the spectrum there. So hydrogen atoms in the second energy level, but what we're getting now is the spectra of other atoms. So this is indicating obviously the presence of calcium, the presence of potassium, and we go down even further, get to cooler ones. We get magnesium and as well some of the other, many of the other elements. And further down, even cooler stars. Some of the coolest, then we're looking at the presence of titanium and titanium oxide, and even the presence of the presence of many other elements as well. So this then is our system of classification that's accepted worldwide these days, where we have O, that is the hottest star. So all of these then are based on temperature. The temperature affects then the spectrum that is produced, and the temperature was also a result of the age of the star. But basically the point of this little video is to show you how temperature can now in fact be determined by looking at the spectrum and seeing what particular pattern of absorptions we get match up with a specific temperature. Of course, the WINS equation is one that we can use in order to work out the temperature of stars. But again, what we find is that the classification based on the spectra is also another method. The spectra also indicates to us what other elements are present on the star. And this provides other valuable information about the star. Now, I shouldn't actually be saying this, but Annie Jump Cannon gave a mnemonic to help people remember the classification system. O, be a fine girl or guy, kiss me. Well, I didn't tell you that, so don't use that mnemonic. O, be a fine girl, guy, kiss me. Okay, that's sexist, so we shouldn't actually use it.